Hey there, economics enthusiasts! Today we're diving into the fascinating world of correlation. In the vast realm of economics, understanding the relationships between different variables is paramount. Correlation is a statistical measure that helps us unravel these relationships, revealing whether two or more variables move in sync, in opposite directions, or have no relationship at all. Imagine you're trying to predict the weather. You might notice that as the temperature rises, people tend to buy more ice cream. This suggests a possible correlation between temperature and ice cream sales. Correlation analysis allows us to quantify this relationship and determine its strength. By grasping the concept of correlation, we gain a powerful tool for analyzing economic trends, making predictions, and formulating effective policies. So, buckle up and get ready to explore the intriguing world of correlation. Let's start by understanding the different types of correlation. In the realm of positive correlation, variables move together in harmony like synchronized swimmers gliding through the water. When two variables have a positive correlation, it means that as one variable increases, the other tends to increase as well. Conversely, as one variable decreases, the other tends to decrease too. Picture this. As the number of hours you study for an exam increases, your exam score tends to rise as well. This is a classic example of positive correlation. The more time you invest in studying, the higher your chances of achieving a good grade. Another example can be seen in the relationship between income and spending. As people's incomes increase, they tend to spend more on goods and services. This positive correlation reflects the basic economic principle that higher income often leads to greater purchasing power. Now let's flip the script and explore the opposite negative correlation. In contrast to positive correlation, negative correlation describes a relationship where variables move in opposite directions like partners in a tango gracefully gliding across the dance floor. When two variables have a negative correlation, it means that as one variable increases, the other tends to decrease, and vice versa. Imagine you're driving a car. As you step on the gas pedal and increase your speed, the time it takes to reach your destination decreases. This inverse relationship between speed and travel time exemplifies negative correlation. Another example can be observed in the relationship between price and demand. Generally, as the price of a product increases, the quantity demanded tends to decrease. This negative correlation reflects the law of demand, which states that consumers are less willing to buy a product at a higher price. To visualize and analyze correlations, economists often rely on a handy tool called a scatter diagram. Scatter diagrams, also known as scatter plots, are powerful visual tools that allow us to explore the relationship between two variables. Imagine a graph with two axes, one representing one variable and the other representing the other variable. Each point on the graph corresponds to a pair of values for the two variables. By plotting the data points on a scatter diagram, we can visually inspect the pattern or trend that emerges. If the points tend to cluster around a straight line that slopes upward from left to right, it suggests a positive correlation. Conversely, if the points cluster around a straight line that slopes downward from left to right, it indicates a negative correlation. The closer the points are to forming a perfect straight line, the stronger the correlation. If the points are scattered randomly, it suggests a weak or no correlation between the variables. While scatter diagrams provide a visual representation of correlation, we often need a more precise numerical measure. This is where Pearson's coefficient of correlation comes into play. Section 5. Pearson's coefficient of correlation, quantifying the connection. Pearson's coefficient of correlation, often denoted by the letter R, is a statistical measure that quantifies the strength and direction of the linear relationship between two variables. It ranges from -1 to +1, where -1 indicates a perfect negative correlation, +1 indicates a perfect positive correlation, and 0 indicates no correlation. A correlation coefficient close to +1 indicates a strong positive linear relationship, suggesting that as one variable increases, the other variable tends to increase proportionally. A correlation coefficient close to -1 indicates a strong negative linear relationship, implying that as one variable increases, the other variable tends to decrease proportionally. A correlation coefficient close to zero suggests a weak or no linear relationship between the variables. Now that we understand the concept of Karl Pearson's coefficient of correlation, let's delve into how it's calculated. Section 6. Calculating Karl Pearson's coefficient, cracking the code. Calculating Karl Pearson's coefficient of correlation might seem daunting at first, but it's actually a straightforward process. The formula involves using the covariance and standard deviations of the two variables. Covariance measures how much two variables change together. It's calculated by taking the sum of the products of the deviations of each data point from its respective mean divided by the number of data points minus 1. The standard deviation measures the amount of variation or dispersion of a set of data values. It's calculated as the square root of the variance, which is the average of the squared deviations from the mean. Once we have the covariance and standard deviations, we can plug them into the formula for Karl Pearson's coefficient of correlation R equals covariance divided by the product of the standard deviation of variable 1 and the standard deviation of variable 2. Let's illustrate this with an example. Suppose we want to calculate the correlation between the number of hours studied and exam scores for a group of students. Section 7. Strong versus weak correlation, the power of the coefficient. To illustrate correlation strength, let's consider a few examples. Scenario 1, R equals 0.95. Scenario 2, R equals negative 0.82. Scenario 3, R equals 0.21. Karl Pearson's coefficient measures only linear relationships. Section 8. Spearman's rank correlation coefficient when order matters. In certain situations, we encounter ranked or ordinal data, for example, student rankings or consumer preferences. Spearman's rank correlation coefficient helps here. It measures the strength and direction of the relationship between two ranked variables. A monotonic relationship means as one variable increases, the other consistently increases or decreases. The formula uses ranks instead of actual values. Section 9. Comparing the titans, Pearson versus Spearman. Now that we've explored both Pearson's and Spearman's correlation coefficients, let's compare their strengths and weaknesses. Pearson's coefficient is the more commonly used measure of correlation and is appropriate when the data is numerical and the relationship between the variables is linear. It's sensitive to outliers, meaning that extreme values can significantly influence the correlation coefficient. Spearman's coefficient, on the other hand, is more suitable for ranked or ordinal data and can capture both linear and non-linear monotonic relationships. It's less sensitive to outliers than Pearson's coefficient. The choice between the two methods depends on the nature of the data and the research question. If the data is numerical and the relationship is expected to be linear, Pearson's coefficient is the preferred choice. If the data is ranked or the relationship is non-linear but monotonic, Spearman's coefficient is more appropriate. With a solid understanding of correlation and its measures, we can now explore its practical applications in economics. Real-world applications in economics. Correlation analysis is crucial in economics. From understanding consumer behavior to forecasting trends, businesses use it for demand forecasting, analyzing price, advertising, and consumer demand. Investors assess asset relationships to manage risk and optimize returns. Policymakers evaluate economic policies, like studying interest rates and inflation. Correlation is indispensable for economic analysis, forecasting, and decision-making. Section 11. Conclusion: the enduring significance of correlation. As we've explored in this journey through the world of correlation, understanding the relationships between variables is essential in economics. Correlation analysis, with its measures like Pearson's and Spearman's coefficients, provides us with the tools to quantify these relationships and gain valuable insights. From predicting consumer behavior to managing investment portfolios and formulating effective economic policies, correlation plays a pivotal role in shaping our understanding of the complex world of economics. By mastering the concepts of correlation, we empower ourselves to make more informed decisions, navigate economic challenges, and unlock new opportunities. So embrace the power of correlation. and continue to explore the fascinating connections that shape the economic landscape.